In this segment, we're going to talk about refrigeration and heat pump cycles. And a refrigeration cycle is a cycle in which you are removing heat from the cold temperature reservoir and adding it and dumping it into the high temperature reservoir for the purposes of keeping that cold temperature reservoir cold. So you've got a high temperature reservoir, and with a refrigeration cycle, this would be your kitchen. And you've got a low temperature reservoir, and this would be your refrigerated space. And your cycle is operating in between that. So it's pulling heat out of the refrigerated space into the cycle itself. That's your QN. And your QN, you could also refer to that as QL, since it's coming from the low temperature reservoir, and it's dumping it out into the high temperature reservoir. That's your Q out, or you could also call that QH, H for high temperature. It's going to require some amount of work input, and it may have a work output, but most of the time you don't have a work output. So my refrigerator doesn't produce any power for me, yours doesn't either, but there are specialized applications, refrigeration cycles used in aviation, for example, that do have a work output associated with them. Typically, though, you don't have any. So in this class, go ahead and assume for any refrigeration cycle or for a heat pump cycle that your work output is equal to 0. In that case, your work net in would just be equal to work in, because work out is 0. And just as a side note, your book, when they talk about refrigeration cycles and heat pump cycles, they refer to work net in as work for the cycle. I like to just say work net in because they use the same terminology for power cycles. They call work cycle work net out, and I just don't want there to be confusion there. So I'm specific about work net in or work net out. Okay, so coefficient of performance, we use a COP with a little subscript R. This is how we this is how we quantify how well that refrigeration cycle does what it's supposed to do. So you can also use a beta for the coefficient of performance. So you see both of those used. I believe your book uses beta. So the coefficient of performance, it's what you're interested in over what you got to put into it. So what you're interested in is pulling heat out of that refrigerated space. That's your QN. And what you have to put into it is your work net in, which is work in minus work out. And if that work out is assumed to be 0, then it's just work in. You can also put this just in terms of heat transfer terms, because for any thermodynamic cycle, work net in is equal to Q net out. So you could put this in terms of QNs and Qouts only. And as a note, unlike for a power cycle with that thermal efficiency for a power cycle, the coefficient of performance is not a percentage, it's an actual number. So sometimes people are a little bit confused as to, well, what's, it makes sense for a power cycle, makes sense maybe the closer you are to 100%, the more efficient that your cycle is. But for the coefficient of performance, what's a good coefficient of performance? Is 7 a good one? Is 14 a good one? What's a good coefficient of performance? And the answer is, it depends. And it depends on the temperature of those reservoirs, the high temperature and the low temperature reservoir. How cold do you need to keep that refrigerated space? And how hot is the environment in which you're dumping the heat out at? So how hot is your kitchen? So it's going to depend on those two things, and this will become a little bit more clear when we talk about the limits on cycle performances as dictated by the second law of thermodynamics, and that we'll talk about in just a few segments. So the answer to what is a good coefficient of performance, that will be answered in a few segments. All right, so when we talk about cycles in this class, we're analyzing them as a black box, but there is something going on inside that black box. And I just wanted to kind of point out, well, what's going on with your refrigerator? So here's a refrigerator. That might be what your refrigerator looks like. Refrigerated space is inside. That's your low temperature reservoir. And the kitchen is your high temperature reservoir. So what you're going to see, we're going to follow the refrigerant as it circulates on through, and that's the cycle itself. You're following that refrigerant around, and the refrigerant itself, your working fluid that's flowing through there, it's undergoing a cycle. So we're going to look up at it at the top, and we're going to watch it flow. So you see it flow? So it's right there, and as it's flowing through that little section right there, the temperature of your refrigerant is lower than the temperature of your refrigerated space. And because heat always flows from hotter to colder, it's going to flow from the refrigerated space, flow from the refrigerated space to the refrigerant. So from hotter to colder. Hotter is actually the refrigerated space. So pulls heat out of that refrigerated space, and now let's follow it on down. So it continues to circulate, and it gets to this little orange box at the very bottom, which is the compressor. That compressor requires a work input. There's your work input, and it compresses your refrigerant. The pressure goes up, and as the pressure goes up, so does the temperature. So now, as it flows through those coils on the back, the temperature of your refrigerant is higher than the temperature of your kitchen, and so heat is going to flow from the refrigerant out to the kitchen, from higher to lower temperature. There's your Q out. And then it continues to circulate on through, and there's a little expansion valve in here. It expands, the pressure goes down, the temperature goes down, and then it gets back down to that temperature that it needs to be within that refrigerated space to pull heat out of that refrigerated space. So there's where your Q ins and your Q outs and your work ins are in your refrigerator at home. But once again, we're analyzing these just as a black box. I just want to give you an idea of what's going on inside that black box, or what might be going on inside that black box. A heat pump cycle. This is a cycle that pulls heat out of a low temperature reservoir and dumps it in a high temperature reservoir, except with a heat pump, the purpose is to keep that high temperature reservoir at a high temperature. So here's my high temperature reservoir. That's my heated house. Here's my low temperature reservoir. There's the cold outdoors. And my box, there's my cycle. Analyzing it like a black box, pulls heat in. There's my Q in from the refrigerated space. I could also call it QL, and it dumps it into the high temperature reservoir, which is my heated house. There's my Q out, and that's my QH. I have to provide some amount of work input. Sometimes you'll see a work output, but typically no. Like I said, in this class, you can go ahead and assume for any refrigeration or heat pump cycles that the work output is 0. And so any work net in that you refer to would just be work in. All right, so we can use the coefficient of performance for a heat pump to talk about how well the heat pump does what it's supposed to do. You can also use gamma. So sometimes you'll see it written as COP, sometimes you'll see it written as gamma. Your book uses gamma, I believe. And it's what you're interested in over what you got to put into it. So what you're interested in is the Q out, and what you got to put into it is the work net in. All right, so the Q out because you need to, you're interested in the heat that's going into that heated space. All right, now by the first law applied to that cycle, work net in is just equal to Q net out. So I could put this gamma in terms of, instead of having it in terms of Q's and W's, I could just have it in terms of Q's, so Q outs and Q ins. And once again, just like that coefficient of performance for a refrigeration cycle, it's not a percentage, it's an actual number. And what dictates whether it's a good or a bad coefficient of performance is the temperature of those two reservoirs. And we'll talk about that in just a few segments when we talk about limits on cycle performance. All right, once again, we do say that in this class we do analyze these cycles as just a black box, but there is something going on inside that black box. So let's kind of get an idea of just kind of how a heat pump works. So you see you've got 4 states in this particular cycle. So your refrigerant is circulating in this big loop. So from 1 to 2, it undergoes a compression process that requires a work in. Pressure goes up, temperature goes up. So you've got this hot refrigerant that's going from state 2 to 3. And as it goes through this heat exchanger, because the temperature of your refrigerant is hotter than the temperature of your inside air, then it heats the house because heat goes from the hot refrigerant to the air inside the house. All right, so heat leaves the refrigerant, it leaves the cycle, and now your refrigerant, it's cooled off a little bit. Then it goes from 3 to 4 through this expansion valve, which is the throttling process. Pressure goes down, temperature goes down even more. Well, there's my Q out. But the temperature at state 4, it goes down even more. And once it gets to this heat exchanger on the right there, the temperature of your outside air is higher than the temperature of your very much cooled down refrigerant, and so heat goes from the outside air into the refrigerant, and the cycle repeats itself. For our purposes, we're not really concerned about those individual steps, but I just wanted to give you an idea of what's going on or what might be going on inside that black box. All right, well, I hope that was helpful, and thank you very much for watching.